Welcome to qnawire.
Okay, so problem number 25 states that a proton is bound in a square well of width 4 femtometers. The depth of the well is 6 times the ground level energy of an electron in the ground state of a one-dimensional infinite square well. The correspond, If the proton makes a transition from the level with energy equals 1 to the level with energy equals 3 by absorbing a photon, find the wavelength of this photon. All right, so let's start with so our potential is given by U is equal to 6E1 1dW, which is the ground state energy of an electron in an infinite square well. So this is given, we get the solutions to this is given to us in figure 40.15b, where we get a square well, a finite square well, with the potential here, U0 is equal to 6E1 1dW. Now it gives us the three energy levels of a particle in this particular box. So for E3, that's going to be equal to 5.09 times E1 1dW. E1 1dW. Okay, then down to about here, we get E2 is equal to 2.43 E1 1dW, and then here E1 is equal to 0.625 E1 1dW. All right, so these are the corresponding energies of a particle in this particular box, in a box with this a finite potential with this potential barrier. Now, if a photon wants to, if a particle is going to be excited from the ground state up to the second excited state, the photon is going to come in with energy called E gamma. That energy has to be equal to this particular transition. So this energy level, this depth here. So in order to excite a particle from here to here, this photon has to be equal to that energy. Now, so we need to know what that energy difference is. So delta E is going to be equal to E3 minus E1, which is equal to 5.09 minus 0.625 times E1 in the one-dimensional well, which is just going to be equal to 4.465 times this energy of the one-dimensional well. Now, so let's go ahead and solve for this energy. So this energy is given by pi squared h bar squared over 2m L squared. So now these are all constants that we know. So the mass here is the mass of a proton. The L is the width of the box. H bar is reduced Planck's constant. So this is going to be equal to pi squared times, that's supposed to be h bar squared, times 1.055 times 10 to the minus 34 joule seconds squared, divided by 2 times the mass of a proton, which is going to be 1.673 times 10 to the minus 27 kilograms times the width of our box, which is 4 femtometers. So 4.0 times 10 to the minus 15 meters squared. So if we calculate all of this, we are given that the energy, the ground state energy of this particle in this box is going to be equal to 2.052 times 10 to the minus 12 joules. Rewrite that a little bit. It's going to be equal to 2.052 times 10 to the minus 12 joules. Okay, and then now we've already figured out that our transition energy is going to be equal to 4.465 times this. So delta E is equal to 4.465 times 2.052 times 10 to the minus 12 joules, which is going to be equal to 9.162 times 10 to the minus 12 joules. Okay, so now we want to know what energy, what's the wavelength of a photon that corresponds to this energy. So the energy of a photon is going to be equal to hc over lambda, the wavelength of the photon. That's not a very good lambda. There we go. So therefore, lambda is equal to hc over E gamma, which is equal to hc over delta E. So this is going to be equal to 6.626 times 10 to the minus 34 joule seconds times the speed of light, c, which is 3.00 times 10 to the 8th meters per second, divided by this energy, which is 9.162 times 10 to the minus 12 joules, which gives you a wavelength of 2.2 times 10 to the minus 14 meters, or 22 femtometers. So the wavelength of this photon is basically, it's on the order of the width of this box. It's 4 femtometers, 22 femtometers. So it's on the order of. So, okay.